Hello, and welcome to another Calcaholic video. Today we'll be going over question 4.9 from James Stewart's Early Transcendentals, topic 3.9. It goes as follows. A runner sprints around a circular track of radius 100 meters at a constant speed of 7 meters per second. The runner's friend is standing at a distance of 200 meters from the center of the track. How fast is the distance between the friends changing when the distance between them is 200 meters? So I'm going to draw out a diagram of what's going on in this problem when time is equal to 0. So this is right before the runner starts running. Right, you can notice that the runner is 100 meters away from the center of the track, and the runner's friend is a further 100 meters away from the runner. And then, at some time during the runner's trajectory, there comes a point where the runner is 200 meters away from their friend. Again, the runner's friend is 100 meters away from the runner's starting position, so that would mean they would be 200 meters away from the center of the track. Okay, so I'm going to focus on the second diagram because that's what we should be looking at. And let's go back to the question, how fast is the distance between the friends changing when the distance between them is 200? Now, what does this mean? Well, it's asking about this right here, this kind of what I've labeled C, because it's the hypotenuse of the triangle which we're going to make. This value right here, the rate at which this changes when it is 200 meters. So, this is the plan to actually figuring out the question. Express the distance in terms of a certain angle on the circle so we can solve for that angle, find the rate at which the angle changes, and then find the relation between the rate at which the angle changes and the rate at which the distance changes. Okay, so step 1. Remember, our final goal is to look for dc over dt when c is equal to 200 meters. But we're going to start by figuring out, if there's any other way we can represent where the runner's current position is. And to do that, we're going to go back to triangles. Now you may be wondering why I've drawn this triangle in this specific way, considering that it doesn't run through what you would think would be the useful points, like the center of the circle. And that's because I wanted to specifically make this a right triangle. Now you may be wondering where the angle part of this comes in. And that's going to come in with the ways that triangle, or this C part of the triangle, differs from the original value, which was just 100. So that was when the runner was here. This distance was just 100. So you'll notice that there's this change in vertical position between where the runner was and where the runner ended up. There's also a change in horizontal position that adds on to this original 100 meters. Using this, we can determine that this C value right here, the distance between the runner and their friend, squared is equal to x plus 100 meters squared plus delta y squared. So, what is delta y and what is delta x? Well, to figure it out, I'm going to return to the unit circle and what the unit circle actually means. So, say we have a point, let's say this one, at angle 60, or angle pi over 3. What does that mean? That point right there is the point on the circle which intersects the side of the angle that isn't at the horizontal. And what else does this unit circle tell us? Well, it tells us that the vertical distance between the point and the axis, or the delta y that we're looking for, is equal to that value up there, which is in this case rad 3 over 2. What this also is r, which in the unit circle's case is 1, times sine of theta, this delta y right here. And that delta y is ostensibly the same delta y that we're looking at, except the only difference is the radius of ours is much bigger. It's 100. So we just have to factor that in to whenever we do it. So it wouldn't just be that delta y is equal to sine theta. In our case, it's equal to r sine theta. This is true for any angle of theta, by the way. So this is incredibly useful for us in solving this problem. Now, what about delta x? Well, that's a little bit more complicated. Delta x, in our case, is the horizontal distance between the right edge and the point which we're looking for. Well, how would we find that? Well, let's take a look at this. On the unit circle, this delta x seems to be the rest of the distance from our cosine to the starting point. So delta x plus r cosine theta at any point is going to be equal to 1. Therefore, delta x is going to be equal to r minus r cosine theta, because remember, the unit circle is just a circle with radius 1. In our case, where the circle has a radius of 100, we have to factor that in. So again, delta x is equal to r minus r cosine theta. So that's the, tricky conceptual stuff done. Now we just have to solve based on what we know. Remember, we know delta x and we know delta y. So we can use this equation to find out what the angle is at the point where the distance is 200 meters. So the first thing we do is sub in our values for delta x and delta y. After that, we sub in the 100 for r. I think I just rearranged the stuff. No, I simplified. Here I just simplified the x part of this equation. And after this, I just distributed the 200 minus 100 cosine theta squared. From here, I just rearranged the whole expression so that it can become more handy to solve. And after that, I just factored out 100 from sine squared plus cosine squared theta. If you remember the Pythagorean identity, that becomes 1. So you have 100 squared plus 1 plus 200 squared minus 40,000 cosine theta, which simplifies out to 50,000 minus 40,000 cosine theta is equal to c squared. From here, we're going to use this to find what c is at this specific point, which if we just plug in 200 squared for c, we can solve this with basic precalculus and algebra knowledge. It becomes that cosine theta is equal to 1/4. So theta is equal to cosine inverse 1/4, or around 1.3181 radians. Now we can move on to step 2. What does this 7 meters per second mean? Well, this 7 meters per second is what we would call in physics linear velocity, or tangential velocity. But here I think it's most apt to kind of classify it as the rate at which the circumference is traversed, or the rate at which the arc length changes. So if we take it to be that, we know that ds over dt is equal to 7 meters per second. Also from precalculus, you can recall that s is equal to r theta. Considering that r doesn't change, if we differentiate both sides, we get ds over dt is equal to r times d theta over dt. We can rearrange this equation to get that 7 meters per second over 100 meters is equal to d theta over dt. Or 7 over 100 radians per second is equal to d theta over dt. Recall that radians are unitless. Now we have all of the pieces. All we have to do is put them together. So to find an expression for dc over dt, we are going to look back at the expression for c squared. So if we differentiate both sides of that, we get 2c times dc over dt is equal to 40,000 sine theta times d theta over dt. Now, what is sine theta? Well, we can use, again, more precalculus knowledge to figure it out. If cosine theta is equal to 1/4, then we can create a triangle with hypotenuse 4 and a horizontal length of 1. Using that, we can use the Pythagorean Theorem to solve for the missing side, the vertical side. That comes out to be radical 15, and thus the sine of theta is equal to radical 15 over radical 16, or rad 15 over 4. So 2 times c, c being 200, so 400 times dc over dt is equal to 40,000 times radical 15 over 4 times d theta over dt. From here, we divide both sides by 400, and then we plug in what we know for d theta over dt. After multiplying things together so that it eventually will cancel out cleanly, we get that dc over dt is equal to radical 16 over 4 times 7, or around 7.778. Remember that dc over dt, the expression of distance over time, will be in meters per second. And now we can use that to finally solve the question. So, we can conclude that the rate at which the distance between the runner and their friend changes when the runner is 200 meters away is about 6.778 meters per second.